I'm Brent Mantooth, and I have recently acquired some Astronomik MaxFR narrowband filters to use with my HyperStar, and they come in a few different bandwidths of 6 and 12 nanometers, and I've been trying to figure out how narrow do you really need to go with these filters. This is just one of the examples I have using these filters of the Crab Nebula, using some of the 12 nanometer bandwidth filters. So a few questions that have come up about the MaxFR filters are, do they produce halos with bright stars? And I wanted to evaluate how filter bandwidth affects things like star size and intensity throughout the image, and how it affects nebula signal and signal to noise, and the contrast. Keeping in mind, filters don't produce signal, they only reduce background. So we'll be taking a look at, so one of the questions is, does the 6 nanometer bandwidth reduce the background more than the 12 nanometer bandwidth? And to look at this, I'll be looking at the Horsehead Nebula, Flame Nebula, and Alnitak star, which is notorious for causing halos in images. So why are fast filters needed? And specifically the MaxFR type of filter is because I use a HyperStar, which provides f2 imaging. And when you look at the specifications for these kind of filters, the documentation that's provided here is typically for the 0-degree incidence angle, so light directly entering the filter. When you get to these low f-stop conditions, the light is coming in from a rather broad cone, so some of the light rays are actually entering at about 14 degrees relative to the filter, and that angle can significantly change the transmission characteristics of the filter. So depending on the filter design, there may be a minimum f-stop that filter is rated for. So if your filter is not designed to pass light for the higher incident angles, then you're essentially throwing away the photons or stopping down your fast optics. So you may have paid for a HyperStar to get f2 imaging, but if you don't put the right kind of filter in there, the filter may be only providing the equivalent of like f4 rates of photon collection. And there's a great video by Quiv the Lazy Geek that goes into some of the physics behind this and looking at several filters, and I'll put a link in for his video here. So one of the questions is lower bandwidth better? Does it provide more background suppression? And what I'll be focusing on today is primarily just the HA signal. As I got into this, that was enough to look at. There's quite a bit to talk about with just these two filters, and I'll be talking about the O3 and S2 filters in the future. So for the first set of images that I'm going to analyze, I used the 0.7 reducer, the Celestron reducer in this case. For those of you that are interested in the details, you can pause the video here and read through all of the hardware that was used. Okay, so to acquire these images, for each filter I collected 3 500-second images with the camera set to unity gain. I did an autofocus run after each filter change. To get flats, I used the Spike-A-Flat panel, and once with all my data acquired, I used PixInsight and the weighted batch pre-processing script to apply image calibration. For all of these images, I applied image registration with a common reference across all the filters, so that way we can actually go back and directly compare what happens and what we're seeing for all of the filters. I integrated the 3 images that were required with no scaling, normalization, or average calculation. So as an example for when reflection happens with these filters. So again, with the 0.7 reducer, here I'm using the ProPlanet 642 bandpass filter. When we look at the Horsehead Nebula, here we have Alnitak, the star that usually will often cause halos in images of the Flame and Horsehead Nebula. We can see that there is a bright region here that is one of the primary reflections caused between the filter and the mirrors in the telescope. If you look carefully, and if YouTube doesn't overly compress it, there is one reflection that you can see here, where you can see the outline and kind of a dark center. There's another reflection that you can see here that it seems to be correlated with Alnitak. Over here looks like another edge of a reflection somewhere. And if you look down here, there's another reflection. I'm not sure where all of these come from, but this is certainly an example of what you don't want to see out of a good narrowband filter. So this is what we're trying to make sure is not going to happen. And I know as I've been looking at some of these reflections and halos, a lot of times they seem off-center and shaped kind of funny. There's a video by Tony and Chelsea Northrup that go into explaining bokeh and standard camera lenses and why sometimes you end up with these funky shapes on the edges versus the nice circles in the middle. So I'll leave a link for that video here because I think it's kind of related to why you see some of these shapes. Let's move on to the MaxFR filters. So here we're comparing the H-alpha 6nm bandwidth filter and the 12nm bandwidth filter. So each of these filters are designed to allow you to collect the H-alpha emission at this wavelength, and they have different bands that are centered at slightly different wavelengths, especially tuned for the fast optics. To help try to make this a fair comparison, I used the EC Soft Stretch script that's provided from the Dark Archon scripts associated with PixInsight. I used the same parameters, so hopefully that does the same extent of stretching. To get to our first question, is there a halo? If you look really hard, you can see that there does seem to be a circle that I can visually pick out, but it's really, really faint, and that only seems to show up for the 6nm filter. If I look over at the 12nm filter, at least visually with this stretching, I can't see it. So to do a little more comparison, I think we need to jump over to PixInsight to do some more numerical type analysis. So here I have the images set up with the HA 6nm and 12nm. So I'm just going to use pixel math, and I'm going to subtract the 12nm from the 6nm image. And when we do that and restretch the image, so if I were to make these the same size, nope, don't want to clone it. Make these the same size. So now we can compare what's the same and what's different. So we can see, especially in here, between the 6 and the 12, it really seems like we have about the same amount of signal. It's really hard to see any nebulosity. However, in the subtraction, I can also see some very faint circles that might be related to the halo that we saw for the 6nm. So is there something there? Maybe, but it is incredibly faint. We also see a little bit more signal coming through in the Flame Nebula, probably because that is not exclusively the hydrogen alpha content here. So to do a little bit more comparison, I wanted to do some cross sections, and the best way I figured out to do that is that I wanted to put the 12nm bandwidth filter in the red channel, and in the blue channel I'll put the H-alpha. So I'm going to make a new image, and we're going to make that a RGB color image. So as we do this, we now have our unstretched image. We'll give it a stretch, and now we have both images registered and in the same place. So what I'm going to do here is save this as a 16-bit TIFF. And just to keep track, I found it was important to put red channel as 12 and 6 so we don't get confused later. I'll now save this as a TIFF, 16-bit, and say OK. PixInsight does have a way to do some cross sections, but I didn't find that it was the best way for me to work, so I downloaded a free program called ImageJ. Now that we're in ImageJ, we need to open the file. So in that case, we have our file name. When the file opens up, it's still in its linear state, and it makes it kind of hard to select the line cross sections. So what we're going to do is a form of stretch using a log transform. So that will get us to a point where we can see it. We can select the line extract tool, draw a cross section. But when we do the extraction this way, it's going to extract the transformed data. So we want to transform this back to the original linear state using the exponent function. Now we can go to plugins, graphics, RGB plot. And now we can see the original image intensities as acquired by the camera. Now for further analysis, I did some of my data in Excel. So I went to data, saved that as an Excel CSV file, and that allowed me to do the more detailed analysis that I was in. So I looked at Alnitak and wanted to compare the two different filters. So I wanted to compare the two different filters. So I looked at the width of Alnitak at the 10,000 intensity line. And it's not quite a full width at half max, it's just saying for a common intensity what was the width that we saw. So I looked at the leftmost and rightmost pixels. You can see that here, see the width in pixels that the star was showing up for. And when we look at that in terms of percent difference, the 6 nanometer filter made Alnitak about 21% smaller compared to the 12 nanometer filter. So it does have an effect towards reducing stars. Now in this case we had a very intense star that ended up saturating the image. So I was also curious what would happen with some less intense stars. So again, here we have Alnitak that was saturated, and there were 3 stars that were kind of in a line that I did a segmented line extraction. I've exaggerated a little bit here. My tracking wasn't the best, so that I had a little bit of elongated stars. I made sure that for the cross section that I'm taking, I'm going kind of across the narrow part of the star where it was elongated. So if we look at the 6 and 12 nanometer filters here, we can see examples of exactly what that looked like for raw signal. I did an analysis of the background of here, and we can see that for the 12 nanometer filter, I had a background of about 90, and for the 6 nanometer filter, about 55. Now, as I said before, this was a unity gain setup, so that makes the assumption that you get one analog to digital unit for each electron. And if we assume that we have 100% quantum efficiency, we can say that that also means that we have about 90 photons detected. And these filters typically claim like mid to upper 90s for that quantum efficiency, so to just simplify it to say, yeah, we had about 90 photons in the background for our 12 nanometer and about 55 for the 6 nanometer. One of the reasons I did this calculation is so I could subtract out that background. And when I subtract out the background, that lets us more directly compare the star intensities that we saw here. So by eye, you can kind of say that it seems like the star intensity is cut in approximately half for each of these stars. And I went through and focused on this one central star and did both a Gaussian fit and Lorentzian fit and found that, yeah, that's about right. You did get a difference of about a factor of 2 between the two filter bandwidths. And it seems like the 6 nanometer had ever so slightly full width half max, but that's probably within about the noise of the measurement. So slightly lower intensity and ever so slightly smaller stars are produced with the 6 nanometer filter. So why do we see some of these effects, and should it affect all stars the same way? Well, when you look at Wikipedia, they have some great examples of the wavelengths that stars emit as a function of the type of star. Some stars emit much more blue, some emit a lot more red colors all the way out into the near infrared. So I've approximately laid the bandpass of the filter on top of the H alpha line here to say that what this filter should do is only pass wavelengths corresponding to here and should be cutting all other wavelengths. So if it's more of a blue star, this filter may entirely eliminate the star. If it's some of these other types of stars, it will probably just attenuate it, and it will attenuate it depending on how much of that star's emission aligns with the H-alpha emission. Some stars will be influenced more than others. So what should we be seeing out of image signal? So narrowbands don't produce more signal, they only reduce the background noise. So assuming that you have the same transmission for the 6 and 12 nanometer filters, you should see lower background but the same nebula signal. So if we were to look at a point here, A, in the nebula, you're getting signal from the H-alpha emissions of the nebula plus whatever sky background. Compared to looking at a spot in the Horsehead that's being obstructed by a dark dust cloud, that should only be sky background. So what I would expect is in the 6 nanometer image, the difference between A and B should be greater because you've eliminated more background. So again, I went back into ImageJ, did a cross section across the image, including the star here at the point A, went across the interface of bright to a dark region and included some dark region. So we can see that we attenuated the star intensity just like we did previously. And here we're looking at nebula signal up to where we have that transition from the nebula signal down to the dark region. And to help kind of guide the eye as to what we're seeing, I used a moving average smoothing function across 10 pixels. So that kind of helps smooth out to see the average signal here. Considering the signal that we're looking at here, if I can measure this background and subtract it out, I should be left with this H-alpha signal. So I subtracted the calculated background from each of our signal traces and compared the moving average calculation to help to visualize these trends. So we can see that we essentially neutralized the background. It's coming out at around 0. And I was very surprised to see that there was very little difference in the nebula signal between the 6 and 12 nanometer, with the 6 being the darker line and the 12 nanometer being the yellow line. And to that extent, we actually saw arguably more signal from our 12 nanometer filter. I was really surprised by this result and started thinking back of like, well, what could cause this? Well, this is a case with the new moon, so there's not a lot of light pollution from the moon. However, I am in a Bortle 5 to 6 zone, so there should be a lot of light pollution that would influence these numbers. I did notice during some of the image acquisition some of the sounds from PhD indicating it was having trouble tracking a star on occasion, so maybe I had some intermittent clouds come through during some of these images. Or for these conditions, maybe the 6 and 12 nanometer filters remove the background to the same extent. And again, they don't create signal. All they do is remove that background. So maybe that's what we're seeing here, is it successfully removed the background using both filters, and we got the same amount of signal. Considering the fact that this is a full 16-bit camera, I used a 500-second exposure, and I was very much saturating the Alnitak star. But for all of that integration, with this F7 configuration for the SCT, that only collects about 60 ADU of signal around the Horsehead. Considering these sensors only pick up these integer values, this 60 ADU is really not much signal, even over that 500 seconds. So that's again where it's really desirable to go to those fast F2 scopes, because I'm sure when we go compare the data there, we're going to see a lot more signal coming out of the F2 scope. Okay, so what can we say about the MaxFR H-alpha filters for using the 0.7 reducer? So based on 3 500-second images at unity gain for an f7 focal ratio in a Bortle 5 or 6 zone. Regarding halos, the 12 nanometer filter shows no halos. The 6 nanometer filter may have a very, very slight halo if you look hard enough for it. Regarding star intensity, the 6 nanometer filter seems to reduce the star intensity by about half compared to the 12 nanometer filter. I can imagine that this could result in some magenta star halos during your processing because you're essentially going to be changing the size of your stars. So that as you start stacking up other narrowband filters, if they have different widths of the star, I could see that causing a lot of fringing around the stars. Regarding background suppression, the 6 nanometer filter did produce lower background levels, about 0.09 ADU per second, compared to the 0.15 ADU per second from the 12 nanometer filter. So if you desired, you could get longer integration times out of the 6 nanometer filter, but you probably really, where I think this is going to have the most influence is if you're really in a heavy light pollution condition. Now, in regard to nebula signal, I feel like when I was looking back at that 6 nanometer filter, I feel like it was brighter and that there was a little bit more contrast around some of these features in the 6 nanometer compared to the 12 nanometer. However, the cross-sectional analysis that we were looking at did not really seem to indicate that there's an actual contrast enhancement for using the narrower filter. So, is this real, or is this something about my analysis? Some things I was thinking about for potential causes for this kind of result is maybe that there was something about my viewing conditions that influenced these results that was just different between the two filters. Maybe the filters are not to specification the way that I anticipated. Maybe there's a flaw in my analysis concept or what the filter bandwidth should be doing to this kind of signal. I was thinking I might get some more data where I acquire 10 or 20 subs, and rather than doing some of these spatial comparisons to look at signal and noise evaluation, look at those stacked subs individually to get the statistics for each pixel. What it seems like from this analysis is the biggest thing you're going to be doing is really reducing those stars. The star intensity seems to be the major difference between the 6 and 12 nanometer filter when used in this F7 configuration. We'll go see what that looks like once we get some of the HyperStar data in the near term. So that kind of wraps up what I have for today. Some of my next steps are I have the data. I'll continue this analysis with the oxygen and sulfur filters with the 0.7 reducer. And whenever I get clear nights again, I'll go out and do some of this similar data using the HyperStar and F2 imaging to see if we get similar results. So if you have constructive comments, questions, or ideas, please leave them below, and we'll see if we can figure out what is the better filters to invest in. Thanks.